Greetings! Welcome to Electronics 2. This is lecture number 41 and I am Razavi. Today we will look at the problem of loading effects in feedback circuits and try to find a methodology for solving feedback circuits more accurately than what we have done before. Last time we briefly talked about this problem and I showed you some examples. So today we want to address that carefully. All right, and for that we really have to go through two steps. One is, how do we open the feedback loop properly to include these loading effects? And number two is, how do we calculate the feedback factor? Today we may not get here, but we'll cover the first topic. So let's go back to the last lecture and see what we covered there. We saw that if I have a feedback system like the generic situation, in this case, voltage. The problem is really that the output and input impedances of this network and this network are not what they should be in the ideal case, right? In the ideal case, we expect the input impedance of A1 to be infinity because it wants to sense the voltage. The output impedance to be 0 because it wants to generate the voltage. This input impedance should be infinity because this wants to sense the voltage, and eventually this wants to generate the voltage also, so its output impedance should be 0. But all of these are not true, so that's where we see problems. As an example, we looked at this amplifier, and we saw that when we want to open the loop, we have this R1 and R2 here, and we don't know what to do with it, right? We expect that because some of the output current of the circuit flows through RC and these two, they should have some effect on the open loop gain, and also because they appear in series with the base, they should also affect the input impedance of the open loop circuit. So there are some ambiguities right now in our mind as to how to open the loop and make sure that these effects are properly incorporated in the open loop analysis. All right, just to show you why these are causing problems, let me give you an illustrative example. So this will show you exactly what the problem is. So illustrative example. So let's consider the voltage feedback situation and assume this is not true and this is not true. Okay, so meaning this is greater than 0 and this is less than infinity. Okay, so we don't have the ideal case here and we don't have the ideal case here. All right, so let's try to find the closed loop voltage gain of the circuit when this output impedance is not 0 and this input impedance is not infinity. All right, we'll see what happens, right? Okay, so here's the situation. We draw the circuit, and we saw that before that to model the output impedance here, we place a voltage source like so, and then a resistance, right? We call this R out. This is the open loop output impedance, and this voltage source is something like A1 times V1. V1 is the voltage that we have here. So this models the feed-forward amplifier. And then for the feedback network, we have a finite input impedance, right? It's not infinity. So we just model that by a simple resistor. Call that Rin. Well, let's call it RF for the feedback network, RF. Okay, and then it generates a voltage, and the voltage goes back and is placed in series with the input voltage source and everything else. So we have that, and then we have this, and then we have this. Okay, and I'm measuring the output voltage in parallel. So this goes here, and this goes here. And our objective is to find the closed loop voltage gain. Now, if the ideal conditions did hold, here 0, infinity, right, then the voltage gain would be just A1 divided by 1 plus KA1, right? But now that we have a finite resistance at the output of the feed-forward amplifier and the finite resistance at the input of the feedback network, certain things might change. So let's try to see that. Okay, so I need to analyze the circuit. Again, circuits 101 should be simple enough, right? Let's go ahead and we say this is V out. So that's V out. And K says I will take this voltage, multiply it by K, and generate a new voltage here. So this voltage is K V out. And then we have a loop here. So what gets to the amplifier, the feed-forward amplifier, is equal to this minus this, as we've seen in the past. So we have V in minus K V out. That enters this amplifier. This amplifier says I will take this voltage, multiply by A1, and generate a voltage here. So multiply by A1. So far so good. In fact, so far we haven't seen any difference with respect to the idealized analysis that we performed many lectures ago. But here lies the problem. We see that we have a resistance at this output, and then we have a resistance here to ground, if you want to call this ground, right? So what happens? You see, I have a voltage source here, I have a resistor here, and I have a resistor to ground, right? So I can model that like this, you see. Here's what we call A1 V1, this guy. Then I have R out, this resistor, and then I have a resistor to ground, so that's RF. And this is V out, right? I'm assuming that you can call this node ground. So you can see what happened, right? We have a voltage divider. So V out is not all of this voltage, as was the case in the idealized scenario. It is this voltage that we have obtained has to be multiplied by this attenuation factor before it gets to V out. So the attenuation factor is given by RF divided by RF plus R out times this, and that gives us the output voltage, right? So let's go back to this color. That's equal to, okay, let's see here. So we now go back to the output, and that's V out. So we should clearly see the difference between this situation and the ideal situation, right? In the ideal situation, we didn't have this factor here. There was no attenuation, so we just got that times A1 equals this, and V out over V1, V out over V in came out to be A1 divided by 1 plus KA1, right? As is the case in any feedback system. But now you can see that V out over V in will not be equal to that, right? There's this factor here, so certain things have changed. Okay, so if V out over V in is no longer equal to A1 divided by 1 plus KA1, what should I say? Should I say this system does not satisfy negative feedback equations? That doesn't make much sense. It should, right? So instead, I say, well, the open loop gain is no longer A1. The open loop gain is some other number. So I can't say it's just A1 divided by 1 plus KA1 is some other number divided by 1 plus K, that number. So we say, as a result of this impedance and this impedance, which are no longer ideal, the open loop gain is no longer A1, is some other number. Okay? So that the output is now different, right? The closed loop gain is different. Okay, so in view of all these issues, we need to have a methodology for opening the loop properly, right? because if we want to calculate the open loop parameters, the open loop gain, we just said that the open loop gain has changed. We need to open the loop properly. All right, so let's talk about that. Opening the loop properly. Okay, so here's the situation, right? I have this, and I need to open it. All right? Okay, so my approach is as follows. I am going to open the loop. So here's A1. The key question is, do you break the loop here or do you break the loop here, right? Ordinarily, it shouldn't make any difference in the ideal case, right? But now we have these loading effects. So actually what we will do is this. We break the loop, and we have a copy of K here and a copy of K here. So this is a copy of K, and this is also a copy of K. And this is X, and this is Y. This is the open loop system now. All right, so take a moment to just digest this idea that I have identified my feedback network, hopefully, right? I call it K. I'm going to make two copies. One copy attached to this side, one copy attached to that side. Meaning, one copy attached to the input, one copy attached to the output. Okay, we still don't know what this means. I will show you shortly. It's not that hard. But one other question that comes about is, what do I do with this node? Should I leave it floating, meaning is it open circuit, or should I ground it? Is it short circuit? And similarly, this node. What do I do with this node, right? So these nodes also have questions associated with them. Okay, so we have to answer all these things, right? So let me just quickly show you how I make a copy of K as an example, and then we go and figure out the rules for these two nodes. Should they be grounded? Should they be left open? And so on. All right, so here's a quick example before we go there. So this is really a separate example in a box, just to get used to this idea. So let's take anything that we have. For example, this one. So we're going to take that. And this resistor divider was connected to this base. So I'm going to make a copy of K and connect it to the input, to the subtractor. See this copy? So that's a copy of K. And I'm going to make a copy and connect it to the output. So here's a copy of K, R1 and R2. All right, so I use a different color to show you that these are the two copies. So here's one copy, here's the other copy, right? So one copy is connected to the input network, namely the subtractor, and one copy is connected to the output port, however it was connected before, right? One thing we still don't know is what to do with this node and what to do with this node, right? These two nodes. Should they be left floating, open? Should they be shorted to ground? What do we do with them, right? So that's the key that we will address next. All right, so now that we understand how to make these two copies and attach them to the input and the output, we just need to figure out what to do with these nodes. And for that, we're going to draw a table. Okay, so here's a table, and we have 4 feedback topologies, right? So we have voltage, voltage. So for voltage feedback, this is what we have to do. We draw those two copies. This goes to the input, this goes to the output, right? And this will be grounded, AC grounded, and this will be left open. So this is open circuit. I'll just write open here so that you know it means open circuit. Okay, it doesn't connect to anything. So here, This was a voltage-voltage feedback circuit, right? So what happens is that this node, which is here, should be grounded. And this node, which is here, right, this output, should be left open. So you just leave it like that. We don't connect it to anything. All right? Okay, so we're going to prescribe this for all 4 feedback topologies. You may ask, why do we do this? Well, we don't prove it here. That's something that we deal with in more advanced courses. But here, we just give you the final result so that you can use these results to analyze these 4 types of feedback configurations more accurately than before. All right, so the next category is we sense a voltage and return a current, right? That's the transimpedance amplifier. Voltage, current. Okay, so again, we have 2 copies of the feedback network. One attached to the output, one attached to the input. And what do we do with these 2 nodes? Well, this will be grounded. This will also be grounded. So we'll see examples of these as we go along, but this is just a table summarizing all 4 cases. And then here we have current, voltage feedback, and for that, it will be like this. So we have a copy connected to the output, and it's returning a voltage. So that will be left open. And we are measuring a current, so that will also be left open. Okay, this little dot means open circuit. Doesn't connect to anything. All right, and finally we have current, which by now you should be able to guess. So here are the 2 copies of the feedback network. And because we are sensing a current at the output, this is left open. As we are returning a current to the input, this is short-circuited, okay, to ground. So these are the 4 topologies that we need to keep in mind when we are trying to open a feedback amplifier. Obviously, we have to identify first which one it is, which one of these it is. And then we also have to identify the feedback network because we have to copy it, right? If we don't know which part is the feedback network, then we can't have a copy here and a copy here. And once we reach this point, we have to figure out what to do with these nodes. And we go to this table. And then we say for voltage, the output of this copy should be left open. The input of this copy should be grounded. All right, just like here. Now I can give you a bit of intuition behind these so that you sort of remember them. This intuition is not very accurate, but it helps us at least remember things, okay? All right, so remember that in a voltage feedback system, like here, K is trying to sense a voltage, right? So it's trying to sense the voltage at the output of a voltage amplifier. So ideally, this circuit sees the output impedance of this guy, which is close to 0. That's why this copy has an input that's connected to 0. Because we think, well, originally this was connected to the output of the amplifier. And the amplifier has a very low output impedance, hopefully, right, this circuit. So now that I want to separate it from the amplifier to have a proper representation, I'm going to short this to ground. Similarly, when I am sensing a current, if this circuit is sensing a current from here, the output impedance of this guy is very high. It's trying to generate a current, right? It's like a current source. So when I want to take this in isolation, when I want to disconnect it from the amplifier over here, I leave it open to represent the fact that it was driven by a high output impedance when it was connected to the main amplifier. All right? And so on. So for example, here, why is this left open? Well, because when this was connected to the amplifier, this amplifier had a very high input impedance, right? So this feedback network would be loaded by a very high impedance, like almost like an open circuit. and that's why I left this open. On the other hand, here I'm returning a current. If I'm returning a current to the main amplifier has to have a very low input impedance. So the feedback network would be seeing a low impedance at its output, so that's why this is grounded. Okay, so this intuition helps you memorize it, or you can just memorize it, right, without the intuition. All right, so here are the 4 cases that we need to remember. We'll go through some examples just so we are clear on how these ideas are applied, and that will show us exactly how we can open any of these 4 feedback topologies properly to make sure all the loading effects are taken into account. All right, let's go over an example. Okay, so I want to revisit this just so that we are very clear. So here's our circuit. We are given this feedback circuit, and we are asked to find all of its parameters, gain and impedances and so on, right? And to do so, to find the closed loop parameters, first I have to find the open loop parameters. And to find the open loop parameters, I have to open the loop, right? I should not have feedback in it. And the question is, how do I do it? All right, so in the first step, I need to identify the feedback network. Where is the feedback network? Well, here it's just R1 and R2. So that's easy. I call this K. All right, so now I go to this row and I say this is voltage feedback. So I have to make 2 copies of that guy. So here's what we have. 1 copy of the feedback network attached to the input, like so, and the other copy attached to the output, R1, R2, like so. Okay, so the output of the amplifier goes to the input of the feedback network. The input of the feedback network is here. And in this case, the output of the feedback network goes back to the input of the amplifier, so that's the output of the feedback network. And we still have 2 ports left, right? This port and this port. So what do? Well, this says that leave the output port of this copy open. This copy, the output port, should be left open. So don't connect it to anything, just leave it alone. And for the input port of this copy, you have to short it to ground. So the input port is right here. This has to be shorted to ground. So this is now our open loop circuit. So we can find open loop gain and impedance and everything else, and then go to the closed loop circuit. So as you can see, in this case, for the open loop circuit, the gain is affected, right? Because I have RC here, but then I have R1 plus R2 in parallel with RC. So the gain is affected. So I can say that A1 is equal to GM RC in parallel with R1 plus R2. All right, see, RC goes from here to AC ground. R1 plus R2 goes from here to AC ground. They're in parallel. Now, this is actually not quite correct. If you remember from Electronics 1, because we have some finite resistance in the base, we would have another term. We would have to write this as RC in parallel with that divided by 1 over GM. And then in the denominator, we will also write this resistance divided by beta plus 1. Okay? But don't worry about it. We're just making approximations here. Okay, so how about the input resistance? So I'll just say approximately so that you remember we are not including this effect here. How about the input resistance? The input resistance is not just 1 over GM of this bipolar device, because the base is not at AC ground. Right? You can see that the base has R1 to ground and R2 to ground. So Rin is equal to 1 over GM plus R1 in parallel with R2 divided by beta plus 1. That's what we discovered in Electronics 1, right? We said that if the base connects to some sort of impedance, then looking from the emitter, we see 1 over GM, but on top of that, we also see the impedance in the base divided by beta plus 1. Okay, how about the output impedance of the circuit? Well, it's not RC, it's RC, and that's in parallel. Again, we're assuming that the early voltage is infinite in these calculations, right? There's no early effect. All right, so I don't have room here. I'll just write it up here. So R out is equal to this resistance in parallel with this resistance, as we saw here. So RC in parallel with R1 plus R2. Okay, so you can see that the feedback network has affected all open loop parameters. All right, because the feedback network doesn't satisfy infinite input impedance and zero output impedance. Okay, so that's one example. We're still working on these ideas, just trying to understand the mechanism or the mechanics for these calculations. So let's go to the next page and see what we can do here. All right, we're going to go over one example that we have seen in previous lectures. Okay, so let me see which one I have here that we can play with. All right, so here's another example. So we saw this before, that I have a two-stage amplifier and I would like to apply voltage feedback. So RC1, RC2, Q1, Q2, and I took this, divided it down, R1, R2. I generated voltage, that's my feedback voltage. And then I said, well, this device can act as a subtractor, so why don't we just connect this here? And that's our main input. Okay, so this is also a voltage feedback circuit. Okay, so we want to break the loop properly, right? I'm interested in the open loop gain and input impedance and output impedance and all of that. So how do we do that? Okay, so remember the previous table said that if we have voltage feedback, we make a copy of this over here, copy of it over here, and then we just have to connect our ports properly, right? So let's do that. We will draw this like this. We make a copy of this feedback network and attach it here, R1, R2, and then we have this one here. And we make a copy of the feedback network here as well, R1, R2. Okay, so this is V in, RC1, RC2, Q1, Q2. And what remains are these two ports. So the table on the previous slide says that for this port, we have to ground it. For this port, we have to leave it open. All right, so that's how we break the loop. We open the loop. Now I can go ahead and analyze the loop, right? Analyze the circuit. I can find the open loop gain, the open loop impedances, and so forth, right? So let's just do that. This is really Electronics 1, so we should be able to do it just by inspection. All right, so open loop gain. How much is that? Okay, well, I start from here. Let's call this X. So it's V out over Vx times Vx over Vin. V out over Vx, the gain from here to here. That's a simple common emitter amplifier. So minus GM2 times this resistance in parallel with this resistance. So that's minus GM2 RC2 in parallel with R1 plus R2. Okay, so that's V out over Vx. And now we need Vx over Vin. How much is that? This is a common emitter stage, but with degeneration. We have some degeneration resistance here. How much is that? R1 going to ground, R2 going to ground. They're in parallel. So the gain of that stage would be minus RC1 divided by 1 over GM of this device plus the degeneration resistance, which is R1 in parallel with R2. All right, that's the open loop voltage gain. So 2 points. Number one, you can see that all the stuff that we learn in Electronics 1 really comes in handy here, right? Otherwise, I have to draw all the small signal models and calculate. This is a pretty complicated circuit, right? But with all the rules that we learned before, we can quickly do this. In fact, I just made a mistake. What was my mistake? My mistake was that the voltage gain from here to here is this resistance divided by that. But that's not true. From here to AC ground, we have RC1 and we have R pi 2, right? So this should be in parallel with R pi 2. All right, so that's the voltage gain. And the second point I wanted to make is that now that we have these 4 rules for opening the loop, we can quickly open the loop and do this analysis, right? It becomes just a mechanical operation without too much thinking, without too much analysis. So it's pretty straightforward. Okay, how about the open loop input impedance? Open loop input impedance. The impedance here, right? How much impedance do we see? Well, we have a bipolar device. We look into the base, and the emitter has degeneration. So from Electronics 1, we know how much that is. That would be R pi 1 plus the degeneration resistance times beta plus 1. So R1 in parallel with R2 times beta plus 1. So one interesting thing that we see here is that the feedback network, which consists of R1 and R2, a voltage divider, plays 2 very different roles as far as the output and the input are concerned. At the output, they appear in series. So you see we have them in series here. At the input, we have them in parallel, both for the gain calculation, this gain calculation, and the input impedance calculation. So that's the way it is, and this would not be easy to predict if we did not know how to open the loop properly, right? We said, okay, we have these 2 resistors. What do? Do we connect them in parallel? Do we connect them in series when we open the loop? And so on. Okay, and finally, the closed loop, the open loop output impedance. So we're just sitting here and looking, so we see RC2 in parallel with the series combination of those 2. So RC2 in parallel with R1 plus R2. So that's the open loop output impedance. Okay, so are we ready to compute the closed loop parameters of the circuit now? We have found all the open loop parameters, but we need one more thing, and that's K, the feedback factor. How much is the feedback factor here? So it's not totally clear, right? Because I'm thinking, is it just R2 divided by R1 plus R2? Well, but here, this impedance is not infinity, right? This is very small, actually. So I can't say, it doesn't seem like it, that I can say it's just R2 over R1 plus R2, right? Well, yes and no. The fact that there is some loading upon the circuit by the circuit is already included in the open loop gain. You see here, because we said that Q1 was degenerated. So it's already included there. So actually, we don't need to include it again. But anyway, we will also prescribe 4 methods of calculating K for the 4 feedback topologies, including all the loading effects. All right, so we'll get there later. All right, let's look at another example of opening the loop. So let's go and look at this example. Again, this is a circuit we have seen in the past, but now we want to analyze it more carefully. So here I have a circuit like this, and I have a 2-stage amplifier, RC1, Q1, RC2, Q2, and actually I have an input current, so I'm trying to build a trans impedance amplifier, In. So I take this output and just connect the resistor between the output and the input. So my feedback network consists of only RF, and that's the output voltage. Okay? All right, so I am given the circuit, and I'm asked to find the open loop parameters of the circuit. So we have to open the loop. And so, of course, first we have to identify the feedback network. So our conjecture is that this is the feedback network, right? And then we go back to the previous table, and we say this is a voltage current feedback topology. So we have to go to the second row of that table and figure out what to do. So let's redraw the circuit quickly and then see what we need to do. So here's the other way. Here's the common base stage at the input. And so we have the common base stage. Then we have the second stage. So the second row in the previous table said that we need to make 2 copies of the feedback network, one attached to the input, one attached to the output. So the feedback network is just RF. So let's make 1 copy of it here, and then 1 copy of it here. Okay, that's all we do. And then we have to look at the second row. The second row said that if you are returning a current, this should be grounded. And if you're sensing a voltage, this should be grounded. Okay, according to that table. Again, I haven't actually proved why this is true, but we just take it. And now I can find the open loop performance of the circuit, right? V out. In this case, I don't have to assume that RF is very large or very small or anything. I don't have to assume RF, for example, is much larger than RC2, right? It's there, I can just include it. So this is RC1, this is RC2, and we call this node X. The base of Q1 is AC grounded, and this is Q2. So let's calculate the open loop gain of the circuit. It's useful, right? This is an exercise similar to Electronics 1, but it helps us understand what the circuit is doing. All right, so open loop calculations. All right, so gain. Gain is again, we are interested in V out over I in. So we say V out over I in, but we're going to write it as Vx over I in times V out over Vx. Vx over I in. This voltage divided by this current. All right, well, we have to do it carefully. This current flows into here, and most of it wants to go this way, but some of it is wasted through RF. So I have to do it like this. I have to say I in is split. How much current flows this way? The current that flows this way is equal to this impedance to ground, RF, divided by this impedance, plus this impedance, 1 over GM. Right? It's a current divider. So if RF goes to infinity, we just get 1 over GM, right? And we get GM times I in. So, sorry, if RF goes to infinity, we get all of I in going this way because no current is dissipated this way, right? Okay, so I in this fraction of I in, hopefully most of I in, flows this way. It arrives here. What resistance does it see? It sees RC1 in parallel with R pi 2. And if you multiply it by RC1 in parallel with R pi 2, that gives us Vx. So Vx over I in is this much. Okay. And then we also need V out over Vx. That's easy, right? So V out over Vx is minus GM2. It's a simple emitter, common emitter. And then these two are parallel to each other, right? So RC2 in parallel with RF. Okay, so that is the gain of the second stage. The overall open loop gain is, so gain, or I can just say, okay, gain, which is V out over I in, is the product of Vx over I in and that. So it's this whole mess. We have a big expression, RF plus 1 over GM, RC1 in parallel with R pi 2. And then times this, there's a negative sign here, I'll just put it over here. We have GM2 and then RC2 in parallel with RF. All right, so that's the open loop transimpedance gain of the circuit, V out over I in. It's always good to check the dimensions to make sure that is correct. The final result is correct, right? The dimension should be resistance. This has no dimension. This is resistance. This is 1 over resistance. That's resistance. So it is correct. Okay, how about the open loop input impedance? Input impedance R in. I'm sitting here and looking here. What do I see? I see 1 over GM1 in parallel with RF, right? By the way, this should be 1 over GM1. So that would be 1 over GM1 in parallel with RF. And the output impedance? The output impedance R out is, we are sitting here looking at this port here. We see RC2 to ground, RF to ground. So it's just RC2 in parallel with RF. Okay, so these are the various open loop parameters that we have found for this circuit. So I hope by now you're comfortable with these prescriptions that we have in the previous page. So let's go back here and see what we had. So we said make a copy of the feedback network, attach it to the input, make a copy, attach it to the output, and then for these two ports we have to figure out whether they're open or short, and that's what we do according to this table. Okay. So far we have covered an example from voltage, an example from voltage current, right? But there are, we can apply to other examples as well. All right. So let's see here. Okay, so one other quick example, just so we are clear. Here's another transimpedance amplifier, RF, right? That was sort of puzzling to us. And how do we open the loop here? Well, just like here, right? This is also a transimpedance amplifier. So we take the feedback network, make a copy, connect to the output, this side is grounded, make a copy, connect to the input, this side is grounded. So that's like this. Very simple. RF to ground, RF to ground, connect the output, and this is the open loop circuit. RF, RF, V out. All right, I'm just following the prescriptions without thinking about it too much. And now I can easily calculate everything, right? The transimpedance gain is I in times RF times the gain gives us V out with a negative sign. So that's the open loop gain. And the input impedance is RF. This concludes the lecture. I will see you next time.